Lecture 79 will discuss a important stress tensor for material science, the stress tensor. It is going to be a second-rank tensor, and there will be eventually a discussion, probably in next lecture, about what this really means in terms of um, it's a bit different from some of the other tensors. Just to give you a little bit of a view forward, we've been working with tensors representing properties of materials. And remember that with stress, you're acting on a material. And sometimes the terminology used for a tensor that's acting as a force on a material, not essentially the thing that's describing how a displacement happens from a force. That is called a field tensor, just because, like, for example, you apply electric field to a material, and then it's the property tensor that ends up giving us so if I have a vector, electric field vector, and then I have a tensor, it's a property tensor that can give me, polarization or something like that. Here, this is a force per unit area we're applying to the material. We create stress, and that stress tensor is going to represent an external force acting on a material, and so that's called a field tensor. So before we get into all that, let's just give you some basics about where it comes from. And again, it's going to come from applying a force on a material, but thinking about a surface that is a particular orientation. So let's imagine that we have our coordinate system, that we have actually a surface which is here. We're going to call the origin O. We're going to call this C, this A, and this B. And it's going to seem kind of complicated, but actually all we're doing is trying to get a generic, simple description that if I put a force on a material and I'm looking at this particular plane, how do I think about the forces per unit area acting on the material in reference to that surface? So let's draw two things. One is there's a normal coming out of this, and then there is some general force that I'm putting on this. We'll call that K. And K is not necessarily aligned to N. So the way we're going to think about this problem now, and the way that you can think about the stress tensor, is the stress tensor is going to be the result of this K is invariant. Let's imagine this force, right, is in some direction relative to this surface. This surface, can move under different cases. So I can rotate it. K is still stationary. The Cartesian is still stationary. And so all that happens if A, B, and C move is that the way that K is resolved onto those surfaces changes. Okay, so that's just the only thing we're going to really talk about here. So let me write K is, K1 x1 hat plus K2 x2 hat. So that means that K1, for example, is already resolved along the x. That way I don't have to deal with that. So I have a particular, K1 that's already resolved along the x direction, for example. So these are forces. This is a force. And of course, sigma is force per unit area, so I have to multiply both by area in order to get the um, the balancing act of my force and then the material response to my force. So on the left side is the applied force, right? And remember, K1 is resolved on X1 but acting on ABC, right? And it has to be balanced by the stress that the material experiences. So for example, that would be composed of the sigma 1,1 coming straight out acting on BOC, which is perpendicular to it, right? But what we're really looking at is, remember, K1 is coming out along the X1 direction, right? It's being applied on the surface ABC. So the only force that you see here is that I need to take the ABC BOC ratio, which is, modifying the fact that the two surfaces are different. So you can think about it as um, the projection, right, of the ABC onto the BOC, right? And sigma 1, 2 is going to be AOC, because remember this is sigma 1, 2, AOC is perpendicular to X2. So that's still sigma in the one direction, but so this first one here is referring to this one, which is direction of force balance, right? The K1 is along the X1, and we're looking at the sigma 1, 1 with the projection of ABC onto BOC. But in this case here, the second one represents the normal, right? Normal to area. So it's the area of AOC acting in the direction of 1. And of course, we have the third term, which is ABC projected onto AOB. So these are all force balance now, just for K1. Of course, I have a similar expression for K2 and a similar expression for K3. So those are all the balanced forces. If you want to project one area onto another, you take the normal of this one and the normal of this one, and the angle between them is phi. And so A prime equals A cosine of phi. So it's just a cosine phi is the angle between the two normals. So the normal, for example, here, right, if I'm projecting ABC onto BOC, then the BOC, x1 is the normal to BOC, and the normal to A, B, and C is n. And so in that particular case, the angle that we're talking about would be the angle between here and there would be the phi that I would be using to resolve. It's be cosine phi of ABC in order to resolve on the BOC. Okay. Now what is that? Well, that's actually just the directional cosine, right? Because that's cosine phi. So that's just directional cosine between the n and the Cartesian axes. So those are directional cosines for n. So I'm going to have one for each axis, L1, L2, and L3. So if you let me clean up here and put this together, I'm going to have K1 equal to sigma 1 L1. Remember, that's just the cosine of phi, plus sigma 1, 2 L2 plus sigma 1, 3 L3. And I'm going to have the same for K2 and K3. And of course, we now know that I can write this as Ki equals sigma ij Lj. So it's actually a very simple expression that just says that I have directional cosines that relate surface ABC to each surface defined by x1, x2, x2, x3, and x1, x3. And that the applied forces, right, that end up being balanced are in sigma ij. This is a vector, this is a vector, and so therefore sigma ij is a second rank tensor. So this is a very simple definition of stress tensor. It just says, and remember ABC is variable, right? So if the force in the same direction, if I keep that the same, I can change ABC, right? And remember, this is the directional cosines from that normal to A, B, and C. So if I shift my surface around, then of course sigma ij gets shifted around. Okay? So even if Ki, the same result same resolve force, the sigma ij change as I move my surface around. So again, just to remember that, I had my surface like that. So that could be one surface. That could be another surface. So this could be, A prime, B prime, C prime. And so even though K may be in the same direction, and I didn't change that, I'm shifting from this area to that area, and of course my sigma ij change because the normal here and the normal here are two different directions. And that is our definite stress tensor, which is really just resolving force onto projected area. And remember what's going on here is that some applied force ends up creating the responsive stress in the material.